human, okay, the human was really thinking about, yes, we might have something, and Giordano Bruno was burned because of that in the church, Catholic Church. And this is why we're going to talk about this new age, new area of new world hunt. And I would like to say also hunts, because we're not just one hunting, we're doing several huntings. And it is not just one world, it is new worlds. And this is what we're seeing here on the right. By the way, I really love the presentation that you did, guys, on the left. It's really fantastic. And yes, it is about us in a suit, unsuitable place to breathe, and searching for life, which is in a flower or something like this. And on the right, we have this artist impression of Ahmed Jabakhanji as a Jupiter-like hot giant discovered lately. And he really gave me graciously to present it in this talk, and also moves. I really thank him for his astrophotography. So, oops, who's doing this? Oh, thank you. Very beautiful painting. So yes, and those hunts started when we started to understand how we form a star, and it's not just a mystery. By now, yani we started by Kant, and after we have this nebular collapse of the molecular cloud, and then we started to see several kind of planets. But the only model that we know can our solar system. يعني نحن we were so wow excited by when we discovered Uranus, when we really observed the planet with ears, Saturn, but we knew then that it is not just years, though the ears, though those are rings. And then come in, we really accepted the idea until recently that we accepted that we have the several flavors for the planets just in our solar system. We have the rocky planets that they are near the star, and the Jovian gas that they are far away from the star, and which is our sun. But then we got this new models, new observation, and new ideas of the formation of a star. And like Dr. Moe Abbas talked in this first talk bill series, in those series, he talked about the stars. And yes, I cannot pass by talking about the exoplanets, or the planets out of our solar system, extraterrestrial planets, without talking about this beautiful eco-friendly system of our universe. And between brackets, we can talk about alien worlds, we can talk about alien planets. Everything that is out of our knowledge is alien, غريب. Everything that is not in our solar system is extraterrestrial, exoplanet, extra biology. So we can talk about alien worlds, extraterrestrial worlds, exoplanets, and so on. So when we understood, if we go back to this slide, when we understood the formation of the stars and the formation of the molecular cloud, and that the medium between the stars is not empty. So the emptiness is not something, a word that the universe is familiar with. We understood that it is very possible and extremely possible, yet it is impossible not to have several stars other than our star, the sun. So if we look at the center of this image, this is a nebula. It can be a molecular cloud. I will not just define how the nebula comes from, but so you see that when we have several clouds, several molecules, the molecules will go down and down under the gravity, and then after a certain density and the gravity, they will collapse to form a star. So the sun-like star, you see that it is on your upper left on the screen, which is, we are going to take just a normal star for the moment, regular, like our sun. It will live, and then after it will be the red giant, then planetary nebula, white dwarf, recycle bin. And if we have several clouds, we will create um, materia, more materia. We can feed more molecular clouds, so we will create a more massive. We will have at the end of the star, at the end of the life of the star, red giant, supergiant, and then supernova, and so on, neutron, black hole, whatever. Star left over. So all of this is full in the space, the big space, hundred of light years of parsec, parallax per second of astronomical units. So if we know that this is how our sun is formed, so we know and we are sure, we observed that we have those in our galaxy. We know that the sun is formed, several stars are formed, and then when we have this pancake shape at the formation of the star, they will rotate to conserve the inertia and the rotational momentum. So afterwards, we will have the formation of planets. So herefore, we will have a lot of planets. And there, when we started the chemistry, when we started to study the chemistry, well, it's not chemistry. So you know by now that I just say that we have mathematics and physics, and the rest of science is details. So when you used to see the Mendeleev table about the elements hydrogen, helium, lithium, beryllium, bore, carbon, azote, oxygen, fluor, etc. You used to wonder, and chemists used to wonder from where those things are coming. And we understood that. We understood that everything is coming until the blue here. If you see them, those kind blue greenish, those are the synthetic one. So everything that is detected, everything that can be reproduced in the labs are coming from life and death of stars. Even what you can have on the planet, and even what you can have on your glass, even what you can have in your mug, even what you can have in your blood. So here we can separate by elements at the creation, from the creation of the universe, the Big Bang, the stars after the explosions, and I'm not going to talk about the synthetic. So once I was an astrophysicist, and not very well experienced, because we can have experience all our life, we learn, quite fairly enough experienced physicist and astrophysicist, I understood that yes, we are part of this whole recycle bin, and we are stardust. But now, how those things are formed? So, as I told you that things are collapsing, molecular cloud collapse, molecular clouds are everywhere, and what you are seeing here are real observation of protoplanetary disks. Pause. When a child is born, بيسموه bebe, he is called a baby, a newborn. When a star is born, بيسموها protostar, bebe. And when we are having a star is born rotating and a disk around it, so في materia in the process of agglomerating to form planets, we call them the protoplanetary disks. So what we are seeing, girls and guys, here, we are seeing إذا بتكون planetary exoplanetary system in the making. Okay, and those are observed by Hubble Space Telescope. هلا بتقولوا لي yes, but we are observing them now. كلهم تقريبا, all of them are so far and away from us. They are really like several light years, 100 of light years. Yeah, but we received them at the stage. Maybe now, if I can go like 50 light years or 6,500,000 light year and travel to those places, they are not that shape. But this is how we receive them. So in astrophysics, I love those paintings. Thank you. So it seems that
Dr.
it's
Cyrine, you can disable annotations from your settings,
okay. So it
from the
seems
screen
that
share settings.
this guy or this girl is really a mess in its head. Okay, so let me just disable. Okay, how can I do it? Annotate. Okay. Um, I can. Where do I go to to disable?
From the
To
screen share options.
yes. Okay. Maybe if I'm sharing, it's fine. It's fine. هيدا بس لحتى تطلع لي more. Disable. Yes. Done.
Okay,
And
thank you, Doctor.
you're
See?
welcome. I can erase. Yes. 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 Sorry for that. For the others. Okay. Just want to erase that. 1 second. Mm, Erase. Okay, so maybe here you're saying, oh, someone wrote, I love you. Yeah, maybe you can present it in a decent way. This is so stupid from you. Okay, so let us continue now. So we were here. We have those real. We started by the theory of the formation of the planetary protoplanetary disks, and we are going to now going into details how we can observe those newborn or already born and adult exoplanets. So when we look at the sky, we just had our eyes and we were so happy and so excited, but we have recent technology and very recent, and it's not stopping. So, how we can discover and observe extrasolar planets? So I decided to, we have a lot of methods, okay? And the methods are really being developed and updated, refined in every second and every day, every week. So I will just speak about the most known, the most detailed, the most used methods. When you think, you can just think about the direct the detection. So you look at the planet and exoplanet. Yeah, I observe it. The transit, the astrometry, the Doppler spectroscopy, detection of circumstellar disk, like I showed you earlier, and the microlensing. I will speak about those. Maybe I start with the astrometry, Doppler, and then direct detection first, and then I inverse the three after the direct detection for a purpose. You will see why. So for the direct detection, we can, if we wanted, for example, one can ask why I cannot just take my telescope or my camera and just look at the star that is far, far away and just search for an exoplanet and take a picture. Well, or just observe it in a telescope. Well, you can try, but you will not succeed just with this method. So the light of a star is 1 million to 10 billion times brighter than the light reflected by a planet. As you know that the planet will not emit by itself a light. So it is nearly impossible for a planet to just man that there's no nuclear power inside of it. It can emit in infrared, but we see later on maybe, but it is really, we need to see how we can dim, how we can use it, this small light to make a contrast, to disable this inequality. So in the optical, for example, if we can see the inequalities between a planet and a star in general. So in light, we have 10 to the power 10 in the optical and 10 to the power 7 difference in mass, and it can be more, and in size it can be even more. يعني أكثر من 1000 مرة 2000 مرة 10,000 مرة. So do you think that we are just as researcher, as astrophysicists, as smart as we are human? Well, not every one of us is smart, apparently. So do you think that we can overcome this difficulty to observe and detect directly the exoplanet? Oh, yes. Well, for example, you can observe the rings of Saturn if you block the light of the planet. You can also observe what's happening around the sun if you take the SOHO spacecraft, and in the center of this slide you can see a real image of SOHO that studied the corona and whatever is around the sun with a coronagraph. Coronagraph, we use it, well, we use it indirectly. Nature is so generous with us because it gave it to us without we ask. On the left, on the right, down, sorry, we have the eclipse. When the moon will eclipse the sun, it is blocking the light of the sun, and we see the corona of the sun that goes millions and millions of kilometers after the sun. So then we can study what is going after the disk of the sun. So scientists use this method, or it was like mechanically, I put a pin, something physically, or they use with kind of the optics, means that they add, like interferometry, they add, they subtract with the phases. Okay, so it is called the 4QKPM phases coronagraph, but you don't want to know that name. What kind of planets we can find easiest with this method when we are blocking the light? For example, now I have a lot of lights in front of me. If you see my studio, I have put like 3 lights, those white lights. So I'm really not seeing very well. If I close my eyes, I'm seeing like circle. If I really need to see you well, I will block the light with my hand. And what I can see kind of planets. برأيكم, what are those planets اللي في يشوفون if I'm blocking the sun? You have to know that the star, sorry. You have to know that each method عندها pros والcons, عندها has the positive things and the negative things. يعني we will have already, I will tell you that we will have a bias, and a bias means that رح نكون موجهين, we will be indirectly have a direction toward detecting this kind of planet or this kind of planet. So for example, if we take the Fomalhaut, when we blocked on the left image on your screen, we blocked the light of the star. We saw that it has a disk around it, and you see the circle around it. And when we observed the system several times, minimum, I remember it was in 2006, in 2009, and I don't know if they did it in 2011, but at least 2 years I was sure. You see that there is kind of a contrast. So we need to have somehow big planet, exoplanet around a star, and not so far, not so close of the star. Because if it was so close, maybe we are going to block also the size with the size of the coronagraph. And if it was so far, maybe we are not going to see it. And if it's so small, it will be completely within the noise of the detection. And this is kind of first bias. Now it is a method of observing. Here we observed with the direct imaging. Akid, it's not just taking a picture. Here we did kind of phases. We added phases, we subtracted phases. We detected 3 exoplanets. I forgot the name of this one, HR960. Anyway, it can be named Toto, Munir, Jamil. It doesn't really matter. But so what's happening, what we are doing here is that the center part was a really very, very huge, luminous, saturating light. And what we did, we dimmed in a way, optical way, and we discovered three exoplanets around it. And you see that the planet D is really close to it. يعني بعد شوي a little bit was really problem to observe it. So this is those are the new methods developed to observe direct methods the exoplanets. So in science, why I'm just developing a little bit the direct method, just to tell you that in science the word impossible is not known, doesn't exist. Maybe it is not very simple, but it's always coming to a solution when we want. So here we have also, you see the point in the center of this image. You have near the center on the upper left, you have a white point, and this is in Beta Pictoris. So here we have a combination, and always it's interesting to observe in multi-wavelengths in astrophysics, because, or in multi-method, and we will see together why. You will see that here we took the star, we took the star out. We are having those disks around it of Beta Pictoris, and we discovered also a planet Beta Pictoris A. And in just comparison, here you have the circle that is cut. I'm sorry, in the image on the upper right, you have the size of Saturn's orbit comparing to what you have here. So, يعني تقريبا this planet is rotating around the same, almost the same orbit as Saturn's orbit around the Sun. So it is really, it's not that easy, and it needed really methods, new methods, but we have a lot of methods indirectly. Sorry, I have to put my 1 second. We have a lot of methods, and otherwise it's going to, so you are seeing my screen. Okay, let me just stop sharing for 1 second, and I will come back to you in a few seconds, because otherwise it is going to bother us if I keep it here. So, okay, stopped, I'm back. And we're here. Okay, I'm back. Okay. Shift 5. Okay. So we are going to look indirectly, and we have a lot of methods indirectly. Let us start by astrometry. So what are the astrometry? So imagine that you have an alien astronomer that is looking at us, and he or she will track the motions, the center of mass, and we'll see that the center of the sun will not rotate in a really fixed position. So we will call it wobbling. So bodies orbiting a star cause it to wobble. So wobble, it's like doing this, like, it's moving with blah, 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 blah. Why? Because when something it's very heavy with something that it is really not that heavy, can cause a shift to the center of mass. Everything is about a center of mass, a center of balance. So here, if we have two person, same weight, same distance that they are playing, so the center of balance will be in the middle of the board. But if they are not, and if the distance is different, so we have to calculate to be able to find the equilibrium, because it is the nature of life to find the equilibrium. And what will happen is that, so you see that even if we have a big star in the center of a system, exoplanetary system, you will see that if we have a small planet, we can detect the small change in the position of the center of the star rotation. But this method was impossible before. You can imagine that the center of a star, if a star is not that easy to detect if they are so far away. So imagine that the small positions of the star, the center of the star to rotate, رح يكون easy to detect. But it is being possible now because we have big telescope, big technology, data science, big treatment, a lot of computational work done, and we understand better and better how things are going in the space. So we can see that. So let me come back to that. So normally, if we detect a star, we know that its position and it's rotating there, okay? If it is not rotating at a certain point that it has to be rotating, يعني there is something that is وإذا عم تعمل wobbling, it's changing, there's something that is obliging the star to move, to change. It can be a binary star. Of course, half of the 50% of the stars in the galaxy are binaries. It can be a planet, it can be a companion, I mean. And then there are a lot of methods to show if it is a planet or not. So this is how we discovered from the change of the position and a lot of combinational method also, that we have a planet 15 light years. It's if you want to travel like with the speed of light, but 15 years, that it is really exaggerating, obliging the star to exaggerate in wobbling, and we just confirm the presence of a star. So what we can do with the wobble back, this wobble is very interesting, because the star is not just an object, a mug that is rotating. This star is also giving us light, giving us photon. And you know that in astrophysics, we just deal with photon or with graviton. Keep it that. j'ai rien dit, ما قلت شيء. So we just, for the moment, we deal with a photon. So we detect wavelengths, infrared, UV, X-ray, or whatever. So we detect what we receive. There is an emitter and there is a detector. So when this star is wobbling because of a companion, مش بس الcenter will move, the emitted thing that will arrive to us will move. Let us see what's happening also and how we can use this wobble. But first, let us talk about the Doppler shift. How we can understand the Doppler shift. Think about a car or an ambulance or whatever. So we have the sound. There's an observer 1 on the left, observer 2 on the right, and the car is moving. You see that the driver is hearing its own voice or noise or whatever, song. And when the sound is approaching the observer 2, the wavelength is compressed. And when the sound is leaving the observer one, the wavelength is depressed, means it's bigger. So those are the Doppler shift for sound. So we said that it's going away on the left, it looks red, and when it's going compressing the wavelength, it looks blue. It's kind of the same what's happening with the wobbling, but this time we're not searching for a dance of the center of mass, we're searching for a change in the wavelength of the light emitted by the star because of the companion. So, and the Doppler spectroscopy is a very interesting one. It was the first method to detect the exoplanet, the first exoplanet. We use it a lot. A lot of numbers of exoplanets are detected with this Doppler spectroscopy. And but not just that, we will see that alone it's kind of, we have something missing. So as I told you, that imagine your star is the ball, the ball, the yellow ball on the right down your image. And this star, a little bit exaggerating, the center of mass is kind of exaggerating. يعني عم بجبرها تعمل wobble مع center of mass like this. Okay, so normally this star, every star with Hertzsprung and Russell, with Herschel, with all the scientists that study the stars, they classified all the stars into O, be a fine girl, kiss me right now, sweetheart, O, B, A, F, G, all the temperature, and every star عندها spectrum. So this يعني كأنه it has its identity, its DNA. So temperature, wavelength, how we say it, composition. So we know that this star, it's from this type, this temperature, it can emit this wavelength at this position, at this speed or whatsoever. But when it is wobbling, we will obtain that at a constant frequency of time, at a constant speed, at a constant period, that we are having a compression of light, the wavelengths that we are going to observe, أو shorter أو bigger. So we will remind ourselves, we will remember that, imagine that I am the star, imagine, and I am emitting. So here something is pushing me. So I'm emitting my wavelengths, I'm pushing it towards you. So my wavelength is going to the bluer, and something is pushing me back, and so it is red. This is a very, very specific method to observe the exoplanet. So here we have a star that is rotating around a center of mass with a companion exoplanet. So the light detected from the star being أو مدفوش لقدام زايح لأنه center of mass أو مشبوق لورا. So we see that when the exoplanet will تبطئ, will decrease إذا بدنا the speed تشدها لورا, we will be like red. So this is a very also interesting method. But as I told you that every method عندها positive side and negative side. Over حطيت أنا 1000 بس هلا بتشوفوا at the end for the numbers for the moment don't I can put 2000 يعني بس إنه you will see that a lot of exoplanets and extrasolar system were discovered by this method. We will talk about numbers by the end with the NASA Gov site and European site. So a lot of are discovered like that. But as I told you that every method عندها positive points and negative points. Okay. So here, if you remember that our astrometry was kind of the wobble on the left image, face on. I'm just taking the example of one planet one star. Okay, we can have double star 6 planets, or double star 2 planets, or double star 1 planet, or one star 7 planets. Okay, but let us take the easiest example. So here on the left, the wobbling, we can have it as an astrometry, but, and you can have it a face on. And on the right side, it is an edge on. What is the an edge on? Is when we are having, or like this or like that, when you will see it, be a good introduction, when the planet will pass in front of the star. So we don't have any idea when we are observing with those compressing and releasing. We don't have any idea about the angle. What is the angle? It's the inclination of the orbit of the planet, and we cannot change. Here, let me tell you a small story. Uh, when I was, one time I was explaining something to my students, and I was telling them that if sometimes, for example, if you have this picture of this galaxy, okay, so this is a galaxy, and we are seeing it edge on. Sometimes when you observe that far objects in the cosmos and they are edge on, you cannot but observing them edge on. It's not like going and observe Mars or Saturn from all the places. You cannot تعلوا راسكم هيك to observe the galaxy from up, to take a picture up, because it's so far away, and to be able to leave the galaxy, our galaxy or our solar system, we need a lot of time. So we are doomed. If we see them like this, if we see them like this, we don't have any idea about the angle, the inclination, and we cannot rotate the observation. So what are the information that we can have? The Doppler technique will only, and only is a lot, will provide us, will give us the minimum mass of the planet, which is really a lot. Why it is minimum mass? Because it contain within it the inclination, the angle, the orbit of the planets around the star. As you know that in our solar system, Pluto, which is in our solar system, from our solar system, it is a dwarf planet, مش إنه غريب. It is not an extraterrestrial planet, but the angle with the ecliptic is 17 degrees, and we have 8 degrees, and we have like 7.6 degrees. Not all of them are in the same plane. So we have this example. So it is very possible that we have it, and most likely we have it. So this is why we say that we can have the minimum mass for the exoplanet. So here, just to tell you how what we discover with the exoplanets method, the spectroscopy Doppler or radial velocity. You see here in red, it's fine. But what I want to show you here, it's fine. You can see that on the upper, you have Mercury, Venus, Earth, and Mars. And you can see that, and on the down axis, we have the orbital semi-major, means that the distance to the star. You see that we can have distances, we can detect distances bigger than the distance to Mars, the distance Mars to the sun. We can have masses 4 times mass of Jupiter. But look at something, what we detect here. I told you, do you remember? Remember. أنا قلت لكم إن إحنا كنا قاعدين كيف تمام, we were happy, yeah, great. We know everything about the solar system. We have the rocky planets near the sun, and the Jovian ones very far. But nature and the universe is so creative more than us, and is so rich more than can we imagine. And we don't know anything yet, because we discovered planets that they are Jovian gases 10 more now, but this is just an example. Huh? You can have all the new numbers, all the new charts, everything on the net, but it's just the science of it. More than 10 times the mass of Jupiter, Jovian, that they are near or close or comparable to the orbit of Venus and Mercury. What? How come? And this is how the observation of exoplanetary observation of the planets, extrasolar planets, oblige us to restudy our comprehension of the formation of our world. Atul, I've been asked why you want to study planets? We are not even eating here. Yes, but I always say that we need everybody on this earth, on this globe, everybody. The scientist, the one who will understand from where we come to where we're going and why we're just here on that point on the earth, rocket planets, that distance, and how come that there is a 10 mass, Jupiter mass, that is near to the sun. And then we developed what is called the migration. If you want, we will talk about them in the question and answer. The radial velocity or Doppler shift or Doppler spectroscopy is a very good method, but it needed, as I told you, it needed the another companion of method, and the easiest and the most used now is the transit. So astronomers, a transit, you all know what is a transit. I think that when someone will transit in front of the screen now, if he's talking, my hand is transiting in front of my eyes. Astronomers also, they saw a lot of transit. They saw the transit of Venus in front of the sun. They saw the transit of Mercury in front of the sun. And they knew that with transit, we can do a lot of things. So they can measure the decrease of the light of the star when a planet will transit or eclipse in front. Why I will not call eclipse? We can say eclipse, okay? But eclipse is in the idea of the public, of everyone. It's when it's a relation, a love relation between the moon and the sun. So this is why the idea is a transit. So what's happening here is you have a star, you have a planet that is passing in front of it. You normalize means that you divide by a value to have a straight line of the brightness of the star. The star is giving you this brightness. And when a planet will pass, it will dim. On the x-axis, you have the time. On the left, you have the brightness. It's dimming. The time of dimming with the time of transit, and we can calculate, you will see what you can have from this transit time. So we started to detect, and also I thank Ahmed Jabakhanji for this image. We started to observe in 2001 with Hubble Space Telescope. And Hubble Space Telescope was not meant to observe exoplanet, but look at that. Let me go back. Okay. No, not here. Here. So if you go back to that, you look that the first hint you have, oh yes, I can calculate maybe the radius of this planet. مظبوط, I can see the radius. I can, yes. Okay, but what you need to know also that studying exoplanet, it's not just about counting them. Okay, we count them, وبعدين. Of course not. Studying exoplanet is studying exoplanet is also characterizing them. شو يعني characterizing them? No, we have to know if they are Jovian, if they are, we can walk of them, if they are like Earth-like planets, if they have atmosphere. So look at here, when you have a planet that is passing in front of the sun, if it has an atmosphere, we can study the atmosphere by spectroscopy or absorption or emission. And this is a very interesting point. So this is how we, not me, it was, I think, very, very 2001, I was like, didn't my PhD yet, but they discovered the sodium within the atmosphere of this planet. And this is another planet they, or also they discovered, and a lot of planets. And for the numbers, I will tell you, but those are shy numbers of exoplanet detection by transit. The boom, the summum started and went by Kepler. Stay tuned, wait. So as every method, here for a change, I put a star with several exoplanets like a Jovian, a terrestrial. So the transit method is also a limited detection. Why? Why? Let us see. Have I put, no, I didn't put the movie because it was so, okay. So it is a problem because remember when it was face on, when the companion was face on, I cannot observe a transit. So I really need, I'm able to observe a transit if and only if the planet passes ما ضروري تمرق exactly in the center, but ده تمرق يا هون يا هون يا هون يا هون. So it has to be in the line of sight. So this is why we combine, always we combine the radial velocity or Doppler shift with the transit. And this is a very excellent method to characterize, to detect, to confirm detection, and so on. So if we look, don't go into the equations. It's a little bit of pepper, salt and pepper and spices are interesting. Just let me explain to you what are translating those equations. So as I told you, if you remember very well, that radial velocity will give me the mass, but it is a minimum estimation of the mass because I don't have my sine I with inclination, who it's kind of unknown, okay? But what I will have from the transit, I will have the radius, and I will kind of derive the orbit. If I have the radius, the orbit inclination, ليش؟ لأنه if I have the radius and I have the mass, I can have the volume. So with several equations, I can have several equations with one unknown, and you know Kepler is T3 over A, ما رح T2 over A3, ما رح نحكي equations بس في relation between them. So we can have the orbital inclination, the mass, the radius, the volume, the density. وهون بنكون وصلنا ل a step, very interesting step for the characterization. It is density, يعني if it is gas, solid, liquid. liquid, don't know if there is a liquid exoplanet, but liquid, total liquid, well, maybe we'll detect total liquid, I don't know. And then we can also characterize the atmosphere. So if it is totally gaseous, maybe it's not worth it to spend like 20 years to see if there is life. We will see the habitability after. So I told you that we have the direct, we have the indirect. We started by the astrometry, the Doppler, and the transit. There is a very interesting method, which is the detection of circumstellar disks. And it is very important because a lot of small exoplanets and rocky one are have been detected on the circumstellar disk. يعني إذا بدكم, if you want to imagine, for example, هيك an idea, the rings of Saturn, حطيتها rings of Saturn because I want to relate it to something very, very funny also. So, but scientifically, the rings of Saturn may be because of, at the formation of Saturn, something went wrong and it was disintegrated, or there is a small moon of Saturn that didn't lasted as a moon because of the gravity, and then it was, And if you see that within Saturn's ring, there is a big emptiness, something that is very, very empty, separation. And here we think that maybe there is something was there and it was empty. So it's very smart, it's not stupid to study the detection of exoplanet within the formation of the solar system. So when you know how the exoplanets are formed, agglomeration, clumps, and when we have the infrared emission, and you know that infrared is a very good tracer for dust, and you know that dust will be grains will be agglomeration for small planetesimal يعني شقف صغار before the planets, planetesimal will agglomerate. Then you see that it's very important to study those circumstellar. And then how Spitzer observed in, I think, Fomalhaut, yeah, various in the temperature of dust, that every size of dust, every composition of dust will give me emission of infrared, variable emission of infrared, different, various. Okay, so having those different emission will give me the thickness, the variety of dust, and if we have planetesimal are increasing and increasing in the disk. I will end by this method, which is the gravitational lensing method. Well, this method is directly from the from Einstein, from the theory of Einstein, that the light is when it is passing through the space, because the space is curved by the masses, because gravity curved the space-time, the light will really move, and a big, massive thing between a star and me observing it will be bended. If you look at the image on the right of your screen, you have a star, an observer, and something that is a little bit heavy. So brown dwarf or whatever, okay? So if you are going to look at it, the light that you are, كأنكم انتوا أخذتوا lens. إذا بتاخدوا, if you take a loop, تكسروه, okay? You want the lens of it, and you will observe the light that is coming from the star. It is virtually increase the light. كيف اللوب طلع هيك بيكبروا, okay? So you will have this ring of Einstein that is increased by this lens, gravitational lens. On the right of your image, you have the observer, and when the brown dwarf is passing in front of a very far star, and then what the brown dwarf or a galaxy or whatever will pass away. So if I can show you this, هلا هون بيتلت my computer. Okay, I repeat it. Okay, what we are seeing here is that we have a very far star. I have the detector or a telescope or an observatory or my eyes, and we are having something very heavy that is passing through in front of my line of sight. So you see on the right bottom, the brightness and the time. We have an increase, suddenly increase, كأنه حطينا loop of the light. And this is how we discovered. But Einstein said that this method is really impossible, because what are the odds that I will be, because it has its cons. And no, I have to be really at that time on a ligne droite, straight line with the line of sight, me, something that is passing, a star with a planet, and a very, very, very background star. And yes, it happened. I will repeat this. Observe the image on the right, up and down. It's just fantastic. It's really, what you are observing here, those are real observation from Ogli 2003, and they were observing a far star, just targeting it, And then a star with a planet passes in front. The star created a gravitational microlensing, and you see that the big short bump on the right left, the green one, is very عندها يعني عندها كتير the profile is so opened, is so increased, and you see that we have blip, two beep, deux zizi, on the spectra of the star. And those are a detection of an exoplanet via gravitational lens. I hope that this will work. It's also a GIF. Well, anyway, you see also that it is, it's not working. So, okay. So, but you got the idea, and it is really, this one is also very, عندها كتير constraints. Why? Because it will have a bias that we need to have really one in the straight. But it's really interesting, other term, that we can detect small ones, small exoplanets, because the star that will pass, اللي هي رح تعمل the gravitational lens, that will create the gravitational lens, will increase the light of this small thing of the exoplanet. And this is really interesting. So, okay, as I told you that those are the major methods. We have like 5 more, and we are developing, and you can also, maybe one of you will develop another method to detect and characterize and travel maybe to those exoplanets. And one of the most sexy exoplanets are the system. So until now, I just spoke about the planet around a star. And you know that in our galaxy, we have more than 200 billion of stars. And imagine that 40% of those stars have exoplanets around them. And you will do the calculation, the math. And if I have in our world, in our universe, more than 100 billion of galaxy, and imagine that we have the same number of planets around the stars in the galaxy. So you do the math. I think that we have more than 10 to the power 20, zero, I don't know, of possible exoplanets. And if we consider that we have just 1 or 2 exoplanets, but here we have a extrasolar system. And you can see that extrasolar system, you can see that we have colors. The star is in the center. We have B, C, D, E, F, G, and H. You see that from half D, E, and G, we have colors. What are those colors? When we talk about exoplanets, of course, we want to count them. Of course, we want the first one to publish for a new detection, for a new kind. And we have papers and to be cited. But what we want to know, if one, they are Jovian, second, if they are rocky planets, atmosphere, oxygen, nitrogen, carbon, habitable, water, okay. So our really idea is to see if those exoplanets are habitable. What is the habitability of an exoplanet? Well, with the years, 20 years, 30 years, we updated with our knowledge the habitability. Okay, so we are not just in a good sun and will not explode, will not be attracted. No, the habitability is one. Is the ratio, if you want, the good relation, the good love relation, love and keep relation, the harmony between the star and the planet. So it needs to have good insulation for the star, for the planet from the star, to keep the pressure, good pressure. Why I'm talking about good pressure? Because the possibility to keep water, the possibility to keep the atmosphere, the possibility to keep the temperature, and to be stable long time to possibly have life on it, to develop life. And this is not a new catalog. I think it is from 2016 or 15. Just an example of red, yellow, and blue. So the conservative habitable zone means that where we are the most optimistic of planets, extraterrestrial planets, where we think that they might be in the habitable zone, those planets. So you see that the big one is the optimistic, because you must know that Venus and Mars are kind of the optimistic habitable zone for the sun. But the blue one, and the yellow to the right, from the half yellow, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, more than 12, 13 possible planets that they are in the habitable zone of their star. But I don't want you to forget, I don't want you to forget that a habitable zone in the solar system, in the extrasolar system for the star, is also has to be combined by the habitable zone in the galaxy. يعني ما لازم يكونوا the stars are in on the arms, for example, because they are having a lot of problems. This is why نحن on هيك inter arms. Okay, so why I have put Saturn, because from those beautiful discoveries, we have this extraordinary discovery, I call it the beast, which is J1407b, whatever you want to call it, the huge Saturn, beast Saturn. It is an exoplanet that was discovered in 2007, but studied like 2-3 years. You can see the papers, scientific papers, and it is a huge exoplanet, but with an enormous ring. So imagine that you have on the right J10407b, it is around the star J10407, and you have it here near the crescent moon. So it's really enormous, and it was fun because قد ما تقولوا إنه شفنا كل شيء, we saw everything with the universe and the exoplanets. We can see a lot of things, and every day you can have a new confirmation and a new discovery. So as I told you, that we need also to characterize the super Earth and to Earth size the atmosphere. وهون بنشوف إنه why we want to do this. At the beginning, we started to detect just the Jovian, the big ones, the hot Jupiters. Why? Because our method كانوا just biased, as I told you. They were not able to detect the small ones. So this is a fraction of presentation to tell you that in comparison to other presence or probability or abundances, إذا فينا نقول, of planets, the Earth-like and super Earth-like planets are not that rare. يعني كنا قبل we detected Jovian because our method of detection. And as for numbers, to just for you اللي بحبوا just the numbers, I did it like 1 hour ago from NASA Gov exoplanets. This is the number of now, today, we have 4,331 confirmed exoplanets, 163 terrestrial, and 1,336 super Earths, gas giant, and the 6 unknown means that we need to observe, مش unknown يعني she not normal, we need to observe more to detect more. And you see that by method. I told you that the beginning, the radial velocity was really إم method, إم الصبي مش بيقولوا. But now we have the transit and microlensing and direct imaging. Those are observing. You see that microlensing, it's 2.5, direct imaging is booming, and it with the technique, it's going also more and more. But you see that transit. With transit, it is since 2015. 2015. Oops. Here I have something. يلا بس هلا افتح البيج الثاني. We are going to wait. Okay. So you saw it all. It was like that. Okay. Oops. Okay. So I had two slides. I had to put them back. Okay. So مش مشكلة. Those transit, all of them were because of Kepler. So Kepler is a satellite that here we have the sun on the right, and it observed just a single place in the galaxy. So here you see that the field of view of Kepler, it really observed بس هيدا المحل. So in this small place for several years, in this small place, وأنا إذا بدي لكم إنه just to be able to compare it in your mind, that the كأنه أنتوا عم تطلعوا بهالقد place هالقد in the field in a football field, okay, in our galaxy. Okay, and until now we are discovering, we are doing the revolution in astrobiology, we are doing the revolution in exoplanets, we are doing the revolution in those kind of studies. But are we done yet? هيدا كل شيء بتلت هون؟ لا مش كل شيء. After several years of struggle, it started in 2007, and then now it is like several times it was postponed, and now it is confirmed. There is, after Hubble Space Telescope, we will have James Webb Space Telescope. Well, James Webb was really a big challenge for the astrophysicists and the engineer and the scientist. Just to compare, I just put the James Webb primary mirror, the Hubble mirror, and a human. So if you imagine the difference between James Webb and the Hubble, Hubble قد ايه صار عامل revolution in science and in astrophysics, and قد ايه عامل for the astrophotography lovers and for the pictures, قد ايه عامل great images of in the sky. So imagine the quality and the nature of what we will have. This one. Second one, Hubble was really very close to the Earth. Now the James Webb will be like 3 times farther than the moon. It is really something, a huge challenge. It will not open until it is in the space. And here I'll try to show you the deployment of the shielding of the Hubble Space Telescope. The solar panels, it needs 5 shielding. The primary will open, and then the secondary. All of this now was successfully done, successfully tested mechanically, thermally, and it will be the biggest satellite sent in space. But in the future, we will have something bigger. I will tell you later. Everything will be automated لحاله, يعني بيفتح at a certain point. And if someone wants, I have a movie of 12 minutes, I can send it to you from the ESA, but I cannot put it here. All the deployment and all the travel of James Webb before it's arriving. So it's done with its environmental testing, and he survived the harsh condition for the rocket launch. What will do James Webb? So we will not just observing exoplanets. We are going to deal also with the formation of the universe. Because you know that until now we are dealing with as I told you, with the photon. So we are going to have more photons. It's bigger, it's nicer. It is nicer, I mean, sensitive resolution. We are going to detect, to characterize the exoplanets, and it will do the in the infrared. We are going to study the atmosphere. We are going to do the coronagraphy also to see and search for the signature of life on that. So here just few images, because I want to give hope, and I want you to believe in yourself. Me, okay, forget my hand. On the left, from mountain from Lebanon, from Deir al-Qamar. Never imagined that I would go to the NASA to work on MIRI, mid-infrared imager. And then this is me. And then when I went there, and the instrument here, that instrument on the right is the instrument I worked on, and it is that instrument, mid-infrared instrument, that is on the satellite, will travel in by the end of the year. So it's like you're having a baby that will go to the space, and that will be observing exoplanets and other things. So here we have also the richness of the space for with new Kepler detection. You have also to know that, maybe you know it already, but I will remind you about that. For example, when you detect a star, and around it you detect exoplanets, you name it with respect to the satellite you're observing, or the observatory. For example, if you observe it with Kepler, you will name it the star Kepler 186. When you observe several planets, you will name it Kepler 186, B, C, D, E, A, F, and that. So this is an orbiting exoplanet, and it is a red dwarf, around a red dwarf. It's a very interesting one. It was observed also, of course, Kepler density method. But what is really interesting, it is that one, it's around a red dwarf. Second, it is 582 light years. So يلا زهقتوا من الأرض, let us go there. No, روحوا لحالكم, أنا ما بدي. No, if we travel with the speed of light, we will have like 582 light years. So now I want to let you breathe a little bit and continue in this mockery, if I may say, that yeah, okay, we observed exoplanet, بلشنا نطلع, صرنا نعدهم. بعدين yes, we characterized them. Okay, في منهم Jovian, في منهم rocky, yeah, okay, and so what? Keep in your mind, the first time a human had consciousness, he or she wanted to know if there is life elsewhere. And this is because we are afraid of death. It's somehow egoist, narcissist for a human. I don't know why. Even medical doctor, why they develop, it's just to develop medicine, develop technology, hybrid, whatever. It's just to push the death. It's like detecting life elsewhere can be as we are okay. So if there's life elsewhere, I don't know why we are scientists. I'm not talking religion now. Okay, as scientists, as if okay, so if there's life elsewhere, so maybe we are not going to die ever. So we are searching for life, and also by curiosity. Because what if we are alone? So we have a responsibility to keep this planet. And what if we are not alone? We have a responsibility to find them. Both of them are really scary. So what do we search if we have a life? So on Earth, the chlorophyll, the photosynthesis are really, really important. So we search for color of the planets. So the color means that the composition in the atmosphere. And once again, maybe you will tell me, but what if It's not about chlorophyll, it's not about green, it's not, maybe, but we always need to search something that we know. So we also need to study the light. We also need to know the power of light. And as I told you, the composition in the transit. We need to see if there is water. We need to see if there is ozone. We need to see if there is methane. We need to see if there is the building blocks of life, as we know, the carbon dioxide, the oxygen. For example, if we discovered a very beautiful, suitable planet, pardon, a suitable exoplanet that is near us and we can arrive like in 1 or 2, 3 years, but we discover that it has no atmosphere like Mars. Okay, so most probably something happened. We cannot go and live there. I will be done in a few minutes. So, but what is life? And how is life? So, life, it's it's a very complicated yet simple and on equation. We just need sponge, sulfur, phosphor, oxygen, nitrogen, hydrogen, carbon. We put them, we leave them in together, and then we wait until they start to be an independent organism. Indeed. And this um, this jump from creating a cell, dead cell, a dead molecule, big molecule, put everything in it and make it work alone. And this is the challenge. Because everything that we do here, scientists on Earth until now, is conservation of energy, is within the conservation of energy. But life doesn't conserve energy. It's how you take something, you work with it, and you expel it in different something. When you start the life, the mechanism, لما تبلش الحياة, and it's related to entropy. So the increase of entropy. So this is it. Yani I have colleagues in France. They work on lab formation of molecules on dust and grains, and the sentence that I said, I find it very beautiful. They say it in French, like we formed everything, we just needed to move or to breathe or to live or to break the conservation of energy. And this is what we don't know yet. And I will finish in two things, telling you that what is waiting for us in the future. Okay, my computer is completely okay. Are you seeing the screen? Can someone tell me if you're seeing the screen?
Yes, Dr. C, we can see it clearly.
Thank you. Because I'm opening now. So yes, this is the site that I really like because it's very well feedback, the exoplanet.nasa.org. And I'm gonna finish with not this, I will finish with that, but before I'm gonna talk about what is waiting for us in the future. What is waiting us in the future? It is that big animal monster, 100 feet, I think, as a radius. So if you think that it's just, this is Sarah Seeger, by the way, MIT, I think. And if you think that James Webb is really huge, wait until this, what was it name? Starshade. It was studied, it was refused, it was accepted, and if not Starshade, they will not stop about searching for exoplanet and extraterrestrial life. And to finish about life, I'm going to talk about the revisited idea about Drake equation. So always I hear a lot of people talking about the Drake equation, and I just want to emphasize on several things. So, and this is something very interesting because the physicist Drake developed its equation a long time ago, 40, 50 years ago, okay? But it was really now updated. Why? Because the numbers are different, the methods are different, and what we don't talk now about the fraction. We talk about the likelihood of, the possibility, the percentage, the probability, okay? So let us go from the left to the right. A, the number of technological species, and here Drake is talking about smart extraterrestrial people, aliens that can discuss, move, travel, etc. Those numbers of technological species that are formed over the history in the universe, observable one, is equal to the rate of formation of stars in the galaxy times the fraction of those stars with planetary system. So this R times F, we call it now the number of habitable planets in a given volume. Because if you have stars with fraction of possibility of formation, those are the number of habitable planets. Then you multiply. So if those fraction of planets have the planets that they are in a suitable for life, NE, then the fraction that they are really have time to develop life, لأنه they can be suitable but they can disappear before developing life بدها وقت to be developed. Then Fi is the fraction of life-bearing planets عملت life suitable for time to have smart intelligence to develop. Fi, intelligent. Fraction times fraction of those Fi to be civilized and to communicate with us, times L اللي هي length of civilization before destroying itself. كل هوديك سو عندي أنا الستار مع ال R, F, P, N, N, E هن number of habitable and the rest times L, the rest يعني F, E, F, I, F هن the likelihood of technological species arising of one of these planets. So, and this is not zero. The number A is not zero if we consider that L is not zero. يعني developed people and species ما قتلوا حالهم when they are developed. But for nowadays, هلا as a scientist, and I'm not talking ufology or unidentified Ayerian phenomena. As a scientist, we are not searching for A. We are not searching for number of technological species. We are searching for number of possibility for a life signature, for biosignature. Means that every bacteria can fart. So if we detect fart, a lot of fart in the atmosphere of an exoplanet, the molecule of fart, we can conclude that maybe we have kind of bacteria. So we are searching for a number A updated that is a biosignature. And believe me that A is bigger than one. And with that, I thank you so much. And maybe I spoke a lot. I'm so sorry. I'm very welcome for your questions. Thank you so much.
Thank you very much, Dr. Cyrine. It's really a presentation of life. Yeah. I really loved it personally myself. Now Dr. Cyrine, it was a great presentation. Myself, I really enjoyed it, and I think everybody did, which is very obvious because how good it was. Now we'll take questions, the Q&A session. We'll start by the questions that we received from Instagram and from the chat. And whoever has a question, he can raise his hand. There's an option via Zoom where you can raise your hand, and I'll give you access to speak. So let's start with a question from Instagram. First question. What other techniques besides transit around a star can we find in exoplanets?
Oh, I said we have the gravitational lens. Other than what I presented here,
Yes. Is there anything other, or these are just it?
no, these are the most used. We have the time transiting variation. Means that if there's a time, if you have several exoplanets, you can detect as time changing in the transit variation. So it's a time TTV, and it's also a transit, but it's small time changing in the curve of the transit. There is we have more three. It's we have let me just tell you ليش أنا ما شو عم سمع يعني. But those are, if you see the website of the NASA, even those are the most observed, the most used. The pulsar, yes, pulsar timing, because the first one was observed by pulsar, but radial velocity. The pulsar timing means that, and this is something very, very weird, because we always thought that the exoplanets an exoplanet has to be around a star like ours, like FG star, and we discovered several exoplanets around pulsar, and a pulsar بيعطي pulse very constant, very efficient, very in a periodic, and when we have the change in the timing of a pulsar, means that we have a companion. And we have also we have something in the disk, I forgot. We have really 3-4 methods that they are emerging, and but the efficiency for the moment is really like less than 1% in the detection. Other question? I don't know if I answered.
I think it's good enough. Thank you, Dr. Cyrine. Another question from Instagram, where okay. How easy is it to detect atmospheric compounds of an exoplanet, and what is the future of this field?
Oh, how easy? Now it is becoming very easy. Well, everything is relative. Nothing is easy in this field, especially when we talk about the atmosphere, because sometimes. Okay, let me talk about spectroscopy, because we observe this mainly with spectroscopy transit. Okay, so I don't have okay, let me take this one. My head, okay, is the star, okay, and I have this planet that is passing in front of me. So imagine that here I have the atmosphere. I will study the light absorbed by the atmosphere that will come to you as an observer, okay? This is a method. Or I will study in infrared the light that is passing here, the second transit from the planet. And sometimes our spectroscope, our detector has to be very sensitive, a very big resolution, because we can really say bad science. يعني فينا نقول له شو ما بدنا, something that it's not the molecule. For example, if we have, let us take an example. If we have, take that, if I detect absorption line from my planet that is passing in front of the star, that it is like that. This is an absorption line. Okay, so here I know that it is 158. I don't know. Okay, I'm saying any numbers, 123, whatever. I know that by the lab, by the book, by the catalogs, that this is, for example, carbon. This is CO2. Okay, so those spectra has to be confirmed by different observation, by more observation, because we need to be sure. Those results will tell me if this planet has a good habitable atmosphere. For example, when they detect the water, the molecule of water. So imagine if it is somehow easy and it can be confused very easily also. So this is why we have to observe with several detectors the atmosphere of the planets. Another question?
Okay, thank you, Dr. C, for this. Here we have Hassam. The floor is yours, Hassam. You can ask.
Yes, hello, Dr. Cyrine.
Hello.
It was a very informative and interesting topic to listen to, and it was a very nice lecture. Thank you.
Thank you so much.
I myself am very hyped on the launch of the James Webb telescope. Are you as optimistic about the promised capabilities of the telescope, or are they overhyping it a bit? Because it had a lot of difficulties and lots of delays after delay, and the hype kept increasing. Will it reach these promised capabilities? And another question, what are you most excited about what the telescope will bring to the table in terms of an unexplained or unclear anomaly in exoplanet hunt? What is there something we are observing but we can't explain with the exoplanets that the telescope will help us understand?
Yes, yes. Well, the first thing I'm excited about the first thing انه launch from Baikonur اول شيء لانه I hope that it will not explode. لأنك I totally agree with you that it was really but they are not overdoing it. It happened that this is a huge telescope وما عم دافع عنه هلا بقول لك وين الغلط يعني. This is a huge telescope, more than 50 countries working, more than 2,000 technician plus 1,000 engineer and 2,000 R.E.D. student, astrophysicist. يعني كنا we ended up by being 7,000 شخص, 7,000 person. كلهم هودي to manage them. Believe it or not, in science we have the egos. And I really decided to work in, I always, before James Webb, I always worked in the theory of simulation. I really wanted to go within to turn things and to work on the satellite to understand. Imagine that if we wanted a filter wheel, if we wanted just filter wheel from Germany, it can take 6 months to be delivered. And we cannot make it ourselves. And if there is a problem مع برغي واحد in the filter wheel, it can wait 6 months من بعدهم. So it's imagine that when you have like 170 companies are working sous-traitant, يعني they are sub-treating consultant. So this was a huge amount of money. هيدي one. Second, this telescope is so big that they didn't knew how to test it at the beginning. It was very promising. Imagine that in 1.5 years, when they did the test, the mechanical test, everything was done. We did the test the VM, the lunch, the temperature, the electronics, the science test. We just wanted معلش حطيت إنه yes تبع الشوك تبع اللunch. So the first time they did it ما فيك تتخيل وقع برغي رجل نزل بالoptical system. They needed to take everything out and to redo the testing. A project $7 billion. So this was the problem of the that late and that late. It is not a very huge مش مكبرينه. They didn't not over do it for that, but it has a lot of problems. مثلا because it's so automated, we are so afraid انه يعلق شيء at L2, and L2 is like 4 times the distance of the moon. So we cannot do anything, and إذا علق شيء mechanical, we'll just have to pray. We cannot go like the Hubble Space Telescope and fix the mirror. And also what we also those are some technical things, but what I'm expecting from it to discover is that more accuracy, as someone asked me about the in the spectra we have a lot of error bars. Error bars يعني أوقات we detect water plus or minus 50% of exactitude. Sometimes there are papers detected like 200% of error. يعني فيكون مي فيكون بطاطا ذات الشيء إنه في. Okay, so I really would like to observe more as number characterization. 3, I'm so excited about the circumstellar disk around the protostars, and with the sensitivity, with the resolution of that, because with this science, when I say I believe, I'm talking science now. I believe and I'm convinced that things are happening within the formation, life, within the formation of a protostar. There's a paper 2 days or 3 days ago, I don't know if Ahmed Jabakhanji is here, he shared it with me about the role of radioactivity and the high energy information of life, in the formation of life. So we are convinced that at this moment of cataclysmic, there is something here formed. This is why also life on Earth is not made on Earth. It's from elsewhere. Those are the exciting things. هلا غير عن البيج بانج والراديشن وهيك. I hope that I answered.
Yes, thank you, Doctor. You are clearly passionate about the launch.
And
about the feasibility.
you have to, and I hope that I will be there. So welcome.
Okay, thank you.
Thank you, Dr. Cyrine. But I have, you said something about the Hubble telescope I want to ask personally.
Yes.
I read a quote from Neil deGrasse Tyson. He said about the Hubble telescope, he said, "Countless women are alive today because of ideas stimulated by a design flaw in the Hubble telescope in the Hubble Space Telescope." We know there was an error when it launched بالmirrors. They fixed it in '93. But what does he mean by the ideas inspired by women? If you know in the field.
It's the lens. It's the lens and that it has an stigmatism.
A concave?
Yeah. So it was stigmat, يعني كأنه كان معه stigmatism. So and they just fixed it because they wanted, the images were not accurate, and how they knew, they observed something that was really.
Chris, I've asked you to unmute if you can ask your question.
Yes, Chris, go ahead.
He lowered his hand, I think.
Okay.
Okay, it's fine. It's not a problem. We can take a question from Instagram. It's fine.
Okay.
How can we know the radius of a planet without knowing its distance to its sun?
Well, the dimming of the transit will give you an idea about the radius. So you
Oh,
don't need
okay.
the distance. You don't need the distance because when a planet will so if I have this shadow, you can estimate the object size from the shadow. No?
Yes, I think so. But it's not always accurate because gravity bends light. I think it's like the
Yes,
eclipse
but
something.
this is why we're having a light curve. It's not just a shadow. So with the light curve is more or less accurate. So when it dims, we can know because it's relative the light curve. We know somehow the diameter of the thing that is passing.
So
And
it's
this is
basically
very
mathematics.
interesting. Yes, but this is very interesting because Savage means that we need to know the exact size of the star
Yes.
also. And this is very interesting because we need to know the temperature, the size of the star, and we need to know the surface gravity of the star. And this is something not very well known. So we know the radius by passing and dimming تقريبا لأنه بنعرف diameter plus or minus 20%.
This is actually very interesting. I think Chris raised his hand again. Chris, are you ready to talk, or we'll take a question from Insta?
Yes, سوري انقطع الواي فاي وقتها قلت اسمي.
لا أنا هيك قدرت. اتفضل كريستوفر.
أول شيء ميرسي كتير، كان كتير حلو السيشن، بس عندي سؤال صغير. إذا ستار عندها كذا بلانت، الووبلينج تكنيك بتمشي؟
Yes, wobbling you mean as an astrometry or a radial velocity?
ما فهمت السؤال.
الووبلينج عندها تو ميثود ما كنت بدي اقسمهم. الووبلينج اوكي انقسم لاثنين: position of the star or the radial velocity يعني كيف عم تتاخر لتعطي الهيدا. Radial velocity for me it's easier if it is two exoplanets, which is the wobbling يعني radial velocity.
Okay. Thank you.
الووبلينج بس لقلك الووبلينج لما الستار تزيح عن السنتر تبعها يصير عندها center of mass. في عندها two methods. أو we calculate the position أو we calculate the emission. And both of them we can use the astrometry.
Okay, thank you again.
If we have the two, I mean 2 or 3.
Yes. We'll take another question from that we received. It's about the chart that you showed. Does the chart showing exoplanets with their masses relative to the distance of their parent star, that one showing a planet 4 times the mass of Jupiter, really close to its star, prove that gas giants in our solar system were born close to the sun and then migrated to a higher orbit?
Oh, this is a very scientific question. It doesn't prove anything because I hope that he or she is listening to me. It can be anything. It can be that our Jupiter gases were formed near the sun and migrated outside. And it can be that they are migrated very, very far and stopped where they are. And it can be they were formed where they are. ليش؟ لأنه why? Because all depend on migration. We have several types of migration: type 1, type 2, type 3. It depends on what we call the viscosity. So the viscosity is the density of the disk and the rotational momentum. Okay, you are rotating, you are forming a planet, and إذا كان التورك, if the torque was أكتر لجوا في ماتيريا بتشبك أكتر you go inside. If no, you go outside. It's about torque, like opening wine opener.
Yes,
And
like a screw يعني
imagine that, imagine that the head of the wine opener is the planet information. So هو قاعد بالديسك حسب كيف قد ايه there are materia in the disk, viscosity يا بيشبوا لجوا يا لبرا. But it can be also that the Jovian planets, some Jovian planets are formed because of the hydrogen and helium, and الكور تبعهم كان كتير كبير بعدين صار to attract some elements like hydrogen and helium, and they were where they are. أكيد plus or minus several kilometers, hundreds, بس إنه. So yeah, it doesn't mean anything. But what we know is that there is a paper for a very good friend, well, someone I know. I wish it was an honor if he was a friend. What's his name? He's an Italian. I think that he showed a possibility that Jupiter was closed and he was kicked out.
Wow.
Yeah.
This is actually shocking to me, kind of.
Yes, but this